Hi everyone, I'm Alex Wein, and I will present this joint work with Pravesh Kothari and Ankur Moitra. So I need to first tell you what a tensor is. A tensor is a multi-way array of numbers. So an order 2 tensor is just a matrix. An order 3 tensor is like an n1 by n2 by n3 cube full of numbers, and so on. So if you have some vectors, we know that you can form a rank 1 matrix in this way. And similarly, you can form a rank 1 order 3 tensor by combining 3 vectors. This sometimes also is called a simple tensor. And then in general, you can define the rank of a tensor to be the smallest r, such that this tensor can be written as the sum of r different rank 1 tensors. Where sum is performed entry-wise the same way as for matrices. And there's actually a lot of different notions of tensor rank, and this one specifically would be the CP rank. So going back to the matrix world for a second, there's various questions we might care about if we want to decompose these. So if I give you a matrix, we might ask, can you compute the rank? And can you compute a decomposition of M into that many rank 1 terms? And when I say efficiently, I mean a polynomial time algorithm. So the answer for matrices is yes, that we know how to compute the rank. So here I'll ignore issues of numerical precision, like if you have a matrix that's rank 10, but really close to rank 9 or something like this, let's not worry about it. I'll basically assume that you can do linear algebra exactly. And also we know how to compute a decomposition. So how would you do it? Well, using like the SVD, you can take M and factor it with the inner dimension R. And if I call the columns of these first matrix the U and the rows of the other matrix V, then this gives me a sum as these are different rank 1 terms. But one thing to notice here is that the answer is not unique, that I can pick any invertible matrix R and sort of put this in the middle to create a different decomposition that's also valid. So moving on to the tensor case, we can ask the same questions. Can you compute the rank? And can you find a decomposition? But here, even the easier question of finding the rank is NP hard, which means maybe it seems at first that we're out of luck, but actually you can still hope to decompose tensors under fairly weak assumptions. The catch is just that we won't hope to decompose all tensors, but just most tensors of with a certain bound on their rank. So to be more specific, we're going to assume that the input is generated in this way, where it actually has kind of a planted rank R decomposition, where the factors U, V, W that make up the decomposition are chosen generically. I'll be more specific about the formal meaning of generic later, but for now, think of it that if U, V, and W were chosen at random, like Gaussian vectors, I want my algorithm to work with probability 1. So not just high probability that tends to 1 for large N or something. I really mean probability exactly 1. So there should be like a measure 0 set of factors where it fails. So in contrast to the matrix case, tensor decompositions actually tend to be unique, surprisingly. Of course, there's some inherent ambiguity, like the one shown here, that you can kind of push scalar multiples around. And of course, you can reorder the R terms and list them in another order. But when I say unique, I mean that the collection of rank 1 tensors that you add together, those are unique. Okay, so going back to this term generic that I used when kind of specifying the type of assumptions I want on the input, we can define this in a formal way. So a predicate is, depending on some formal variables, is going to be true generically. The meaning of that is that there exists a polynomial that's not identically zero, so that as long as that polynomial doesn't vanish on your input, the property or the predicate must hold on the input. And so if you have this, it means that the predicate has to hold for almost all x, all but a measure zero set. And an instructive example to think about here is that if I choose n different vectors in dimension n, then generically, these will be linearly independent. This is like a very intuitive fact, but how do I prove this or frame it in using the definition from above? Well, linearly independent would just mean that the determinant of a certain matrix is not zero. The matrix whose columns are these n different vectors. So here, to fit this into the above definition, the formal variables are all the entries of all the u vectors. So there's n squared of them. The predicate I'm talking about is whether or not these vectors are linearly independent. And then the way to verify the definition is to take g of x to be this polynomial. That's the determinant. Okay, so taking a step back, why do we care about tensor decomposition? I think it's a well-motivated question in its own right, but there's also some useful applications of these. So here's a list of some areas where this is used. One place where it comes up is when applying the method of moments. So imagine that you have a bunch of samples drawn from some distribution. These are high-dimensional samples, and you want to learn something about the underlying distribution. So one thing you might start to do is to estimate the moments of the distribution from your sample. The first moment, second moment would be like the covariance matrix. But then if you want to go into the third moment, this will be a tensor. And so in certain settings like Gaussian mixture models, the first two moments do not contain enough information to actually learn the parameters of your distribution that you want. And it's exactly because matrix decompositions are not unique, as we saw earlier. But the third moment turns out to be enough, and the tensor decomposition is can be used here. So going back to the question at hand, here is going to be the goal for me. Given an n by n tensor, I'm going to assume it's kind of a square tensor to keep things simple for now, although the results will apply more generally. And we're going to assume that it has this planted rank R decomposition where the components are chosen generically. The goal is to have an algorithm, a polytime algorithm that will provably recover the rank 1 terms. Okay, so what's known about this problem? For what value of R can we hope to solve it? Well, the first thing to say is that as long as R is smaller than roughly n squared, the planted decomposition will be the unique rank R decomposition, which means that in principle, you can hope to solve the problem, but that doesn't give you a fast algorithm. When it comes to algorithms, there's this very classical method that's called either simultaneous diagonalization or sometimes Genrik's algorithm that works when the rank is less than the dimension. So that's what we call the undercomplete case. Whereas overcomplete will be when R is bigger than n. And the overcomplete case has been kind of a big challenge for a while. So eventually we found algorithms that can go into a slightly overcomplete setting. And then more recently, there was a breakthrough where we can get now a constant times n. And our result is trying to kind of push this to the limit. So what we get is the rank can be essentially 2 times n. or rather, 2 minus epsilon times n, where the runtime will depend badly on epsilon, but polynomially in n. More general for tensors that are not square, the result is really instead of 2n, it's more like the sum of the two larger dimensions. And all of these algorithms have sort of a funny feature, which is that they only actually use a constant number of slices from the tensor. And yeah, we don't know how to fully exploit more slices if we're given them. And so all these algorithms also apply to tensors that are, n by n by constant. It's worth contrasting this to the case of random components. Random components meaning the components are not generic, but rather imagine they're drawn IID Gaussian, and the goal is just to succeed with high probability. So probability converging to 1 as n goes to infinity. Here you can actually do much, much better. You can reach a rank that's like n to the power 3 halves. So there is seems to be a substantial difference between the generic versus random case here, and I'll come back to that later. So let me try to give you some proof ideas for how one may try to solve this problem. I think a helpful way to think about it is to first consider this easier task that we'll call rank detection. This just means given a tensor, again with components chosen generically, instead of trying to recover the terms, let's just try to find the rank, just to compute R. So some previous work did manage to kind of reach the overcomplete case here. The PhD thesis of Madalena Pursue gets to 3 halves times n, and then we'll improve this to basically 2 times n. And the main idea, the approach here is going to be constructing what we call a flattening. That's going to be a map that takes in a tensor and outputs a matrix. And the hope is going to be that the rank of the tensor is directly related to the rank of this matrix somehow. In some sense, tensors are hard to work with. We don't know how to do anything algorithmically with them, so we are trying to reduce to the matrix case. So what type of flattening might you want to consider? Well, first one to maybe talk about is what we call the trivial flattening. So you can take an n by n by n tensor and flatten it to an n squared by n matrix just by taking the different slices and stacking them on top of each other. So what does this do when we transform a tensor into a matrix like this? If we start with a rank 1 tensor, you can see that we will get out a rank 1 matrix. So what happens if we start with a rank R tensor? Well, we'll get, this is a linear map, so we'll get the sum of R different rank 1 matrices out, which is something of rank at most R. And in fact, it will be rank R as long as R is less than or equal to n and the components are chosen generically. So you can see here why R equals n is kind of a bottleneck, right? Because this tall matrix has only n columns, so definitely it cannot have a rank any bigger than n. And so this basically solves rank detection up to, rank less than or equal to n. This is the undercomplete regime, which has been kind of understood for many years. And the main challenge here is going to be to beat this by a factor of 2. So we need to kind of overcome this bottleneck of rank R equals n. But before I talk about how to improve it, let's say a little bit about how would you go actually from rank detection to decomposition, because the same sorts of ideas used in this example will, are also used in our actual result. So what's the point? We have this matrix M that we've constructed by flattening the tensor, and it's the sum of these R different terms. And the goal is to recover those vectors. So from the previous result, we know that this thing is going to have rank R. And the idea is to look at the column span of this thing. What is in the column span? Well, the column span is going to contain, these things. It's going to be the span of the individual columns that appear in those rank 1 terms. Okay, and why is the column span equal to this? Certainly all of those are contained, or which way does this go? That certainly the columns, everything in the column span is a linear combination of those things. But by dimension counting, since we know rank is M, rank of M equals R from the previous slide, it actually has to contain all of them. So the column span will be precisely the span of those vectors. And if we can recover those vectors, we're basically done. So we're kind of reduced to this question of, you have a linear subspace and it contains some particular vectors in it, these vectors that have a special rank 1 form, U tensor V. And we want to pick those out from the subspace. In other words, if I think of this thing U tensor V as being shaped as a matrix rather than a vector, you can imagine that we're given a linear subspace of matrices, and we want to find rank 1 matrices inside that subspace. And this is actually a problem that's been studied recently in this very nice work. That there is actually a polytime algorithm to do this as long as the rank, the number of these rank 1 tensors you're looking for is smaller than something like M times N. And in fact, as an aside, with some of my PhD students, we improved the constant on this result of it. So that's essentially the strategy, is to use this type of algorithm to pick out the certain vectors in the column span. Let me now address the factor of 2 improvement. How are we going to do better than the trivial flattening? We're going to use something that based on this idea that goes back to Landsberg and Ottaviani, which has either been called Young flattening or Koszul-Young flattening, or perhaps both. I think there's a subtle distinction between the two that I won't try to get into. But here's the construction of the better flattening. It's going to have these 2 parameters called P and Q. It's again going to be a linear map that takes a tensor, outputs a matrix. And let me first tell you what it's going to do on rank 1 tensors. So if you input a rank 1 tensor, it's going to output this thing. So a certain matrix that depends on U, Kronecker product with this UV transpose. So essentially the second and third modes are being flattened in kind of a trivial way, but the first mode, the U, is being flattened in a strange way, where it's instead of going entirely to the columns or rows, it's going to be split between them. So you can think of this A as being kind of a roughly square matrix. And the construction of A is something that may look a bit strange, but it's, a particular kind of combinatorial matrix. It has rows indexed by subsets of Q that have size P. It has columns indexed by subsets of Q that have size P plus 1. So you can see the example on the right here for P equals 1 and Q equals 3. And so on the row you have a subset, on the column you have a subset, and you put a non-zero entry there if this subset is a subset of that subset. And then the entry of U that you put in there is kind of that missing element you need to add. And there's also a plus or minus one sign that I won't get into how it's chosen. And so it's kind of key for this construction that the matrix A is somewhat rank deficient as you take, for example, as you take Q large and P to be roughly half of Q, it's rank deficient by like a factor of 2. And that's where our factor of 2 improvement comes from. And so this, again, kind of has this rank detection property that we hoped for, that the rank of this resulting matrix we've created is, some fixed number times the rank of the original tensor. So that's the key idea for, going into this overcomplete regime. And then some more work is needed to actually do the decomposition part. But again, the key idea is somehow searching in the column space for vectors that have a particular right type of structure. It's helpful here that somehow the A matrix is somewhat sparse and has a lot of zeros in it, especially as P and Q are larger. To wrap up, a big question that remains still, I think, is whether R equals 2n, is this really the limit for efficient algorithms? Can we do any better? It's tantalizing to think we might be able to do better because for random tensors, we know these much better algorithms. And also for order 4 tensors, right? I've talked about order 3 in this talk, but for order 4, there's actually no gap between random and generic. Both need rank roughly n squared. So this all kind of points to perhaps thinking that order 3 tensors with generic components, you should be able to go all the way to R is n to the 3 halves. But there's kind of a good reason why even order tensors are easier, which is that you can flatten them in a square way. Whereas for 3 by, n by n by n tensors, there was this asymmetry and it was hard to flatten them in a useful way. So there are actually some lower bounds known on what's possible using flattenings of this style. So building on some prior work, if we restrict ourselves to linear flattenings that take the same form that we used, where it's, some matrix A depending on U, and then you flatten the U, V and W in the trivial way, then actually 2n is the limit for this. You can't do any better. And if I allow general, any linear map from tensors to matrices, you still can't go past 6n. And we consider even a more general class of plausible approaches where you use somehow degree D homogeneous polynomials. But even then you get stuck at some constant times n, where the constant will depend on D. So this kind of seems to suggest that perhaps you cannot actually get to R to, n to the 3 halves, or at least you'd have to use a very different approach in order to get there. But we still don't really know for sure whether 2n is the limit or perhaps a different constant times n. So that, remains kind of a mystery still at this point. Another sort of suggestive result is that I mentioned the work of Koiran, which is a rather different algorithm for tensor decomposition that goes up to, rank of 4/3 times n. But this also seems to have a very natural barrier at 2n that it will definitely stop working at that point. So this perhaps, I think it's quite possible that 2n actually is a limit, but we don't know for sure. All right, I'll stop there. Thanks a lot for your attention.